Hello YouTube and welcome to the third unit, polynomial graphs. So in this unit we're going to be covering everything about polynomial functions and equations. So we're going to be learning about concepts such as leading coefficients, end behavior, degree, multiplicity, all of that good stuff. So let's get straight into it. Let's go on to understanding polynomial functions. Let me turn on my laser pointer. So the polynomial equation is in the form of p of x, and there are n terms here, and each term consists of a coefficient and a variable. And each one of these variables has a power attached to them. If you notice in the x to the n, there is a power n, and also in this x over here, there's a power n minus 1, and so on. Usually, you're given equations when you have a descending power, so normally this would be n minus 1, like that. But sometimes you're also given polynomials where it's not in order and you have to do that yourself, which is fine. So the degree of a function refers to the highest exponent of a variable. That would be, so whatever variable has the highest exponent, that would be the degree of the function. And you would write that, in this case, would be degree n because n would be the highest exponent. And the coefficient of the greatest power is the leading coefficient. So whatever the coefficient is of the leading power, it would be your leading coefficient. So in this case, it would be a, because it's right attached to the variable with the highest exponents. So let's move on. Examples. So we're given the function p of x is equal to 3 times x to the 5 and so on. And notice how each one of these powers is descending here. So it starts at 5, then it goes to 4, 3, 2, and then 1, and then 0 at the end. That's pretty much what you're going to be given most times, but always be prepared for anything else, which I'll discuss in example 2. But for now, let's talk about the degree. So the degree is whatever variable has highest exponent. So I'm noticing here, the highest exponent is going to be 5. So our degree would be a 5. So it'd be a degree 5 polynomial. And the leading coefficient, whatever is being multiplied into the x to the 5, so it'd be a 3. So the leading coefficient would be a 3 right here. Perfect. So let's move on to the second one. So we're given the function f of x is equal to 2 times x squared and so on. So notice this one, our powers aren't in descending order. So it starts off at 2 and then it goes to 4, 1, 3. So it's a big mess here. So that's fine, but we're just going to have to focus on the highest exponent here. It doesn't matter. So for our degree, let's look at the variable with the highest exponent. So I'm noticing this x to the 4, that's going to be our highest exponent here because there's no other exponent higher than 4 here. So our degree would be a degree 4 polynomial. Perfect. So, and for our leading coefficient, it would just be whatever is attached to the x to the 4. So it'd be a negative 9. So you can't just say 9. You have to include this negative here. So it'd be a negative 9. There we go. So end behavior. Let's talk about this. So now that we know leading coefficients and degree, let's talk about end behavior. So the end behavior of a polynomial function is the behavior of a graph as it approaches negative or positive infinity. So it's basically the behavior of the graph as it stretches out from one end to the other. So this point says the end behavior depends on both the leading coefficient and degree of a polynomial function. So you'll be able to determine the end behavior of a polynomial function if you know the degree and the leading coefficient, which all affect the end behavior of a polynomial function. So the last point here says, when discussing end behavior, we use quadrants to identify the behavior as it approaches negative or positive infinity. So this is what I'm talking about, the quadrant system. So this top right half is quadrant 1, and then it goes to quadrant 2 on the top left here, and the bottom left here, quadrant 3 and quadrant 4. So you can sort of remember it as, what's the right word, counterclockwise, I believe. So you start off at quadrant 1, you go to quadrant 2, quadrant 3, and quadrant 4 over here. So let's move on to some examples. So we're given this function here. I don't know if you guys can see that clearly, but it's our normal y is equal to x function. But now we have to figure out the end behavior. So when we're talking about end behavior, we want to read it from left to right. We always want to go left to right for end behavior. So I'm noticing here is it extends all the way down to quadrant 3 over here. If you remember from the previous picture over here, quadrant 3 is down here. So it goes from quadrant 3 all the way up to quadrant 1. So let me actually get my pen over here. So it goes from quadrant 3 to quadrant 1. Notice how we're reading it from left to right. We're going from left to right. That's what we want to be doing. So let me clear this out now. Yep, there we go. Let me turn this off. Get my laser pointer back on. So that would be reading as quadrant 3 to quadrant 1. So it extends all the way down to quadrant 3 as it approaches negative infinity, and it goes to quadrant 1 as it approaches positive infinity. Perfect. Let's move on. So we're given this quadratic here, and it looks like as we go from left to right, so as we go from negative infinity, it's going up all the way to quadrant 2, and as it approaches positive infinity, it goes all the way up to quadrant 1. So we can actually, let me write that in here. So we go from quadrant 2, let me just, quadrant 2 to quadrant 1. Basically what this is saying is as x approaches negative infinity, we're going to quadrant 2, and as x approaches positive infinity, we're going up to quadrant 1. So let me erase this, turn this off. So there we go. It'd be from quadrant 2 to quadrant 1. So hopefully that makes sense. Let's move on. So the end behavior of polynomial functions. So what we talked about is end behavior of just functions that we know, but what about for polynomial functions? If the degree of the polynomial function is even, so if you remember degree is basically the highest exponent on the variable, if that is even, then the end behavior goes from quadrant 2 to quadrant 1. Now, if the degree of the polynomial function is odd, then the end behavior goes from quadrant 3 to quadrant 1. So basically the highest exponent, if it's odd, then it goes from quadrant 3 to quadrant 1. But if the highest exponent is even, then we go from quadrant 2 to quadrant 1. Now, we're going to discuss if your leading coefficient is negative, then the end behavior is flipped. So if you have a negative leading coefficient, whatever is being multiplied into your highest exponent variable, then everything gets flipped around. And you can think of this as a vertical reflection, but it's not really a vertical reflection, but you can think about it like that. So if your leading coefficient is negative, then the end behavior is flipped. So for example, if your end behavior would normally be from quadrant 2 to quadrant 1, it would normally now go to quadrant 3 to quadrant 4. And that makes sense. If you're normally, so let me draw this out here to visualize. So if you're given the normal Cartesian plane, and you have a function that goes from quadrant 2 to quadrant 1, and if the leading coefficient is negative, that means everything's being reflected, and you're just going to be going from quadrant 3 down to quadrant 4. And that would be for, so let's clear this out. Now, if your end behavior would normally be from quadrant 3 to quadrant 1, it would now go from now be quadrant 2 to quadrant 4. So what this would look like is, again, if we're given the Cartesian plane, and let's say we're given the function, let's say we're given this function, notice how it extends from quadrant 3 to quadrant 1. If this function had a negative leading coefficient, then we would be given something like this. And it would now extend from quadrant 2 to quadrant 4. There we go. So that is basically end behavior of polynomial functions explained. I'll be making a video doing some practice work on this, so don't worry. But for now, let's hop on over to Desmos and do some cool things. So now that we learned everything there is to about leading coefficients, end behavior, and all that stuff, let's try to construct some functions. So I'm going to give the function p of x. Let's say p of x is a even degree. So we're going to say x to the 4 plus 2x cubed. Let's just make up some numbers here. Minus, let's say 7x squared plus 6x minus 4. Okay, perfect. So we've made up our function p of x, and notice the highest degree is x to the 4. So it's an even degree, so that means we're going to be going from quadrant 2 to quadrant 1. And that does make sense. It does look like we're going from quadrant 2 to quadrant 1. Basically what that means is as x approaches negative infinity, we're going to be going from quadrant 2, and as x approaches positive infinity, we're going to be going all the way to quadrant 1 over here. Now, what if our leading coefficient was negative? So let's say this was a negative 3. Now this changes everything. Notice how it flips the entire thing. It does flip it. And our end behavior now, instead of being from quadrant 2 to quadrant 1, it goes all the way from quadrant 3 to quadrant 4, because as x approaches negative infinity now, we're going to be going from quadrant 3, and as x approaches positive infinity, we're going to be going to quadrant 4. And the same thing applies for odd degree functions. So let's say we're given another function, f of x. Let's say we have an odd degree. Let's say we have x to the 7. Notice 7 is odd, and let's just attach a coefficient for fun. Let's just say 2. Let's just make up another number. Let's say 5x to the 6 minus 3x to the 5 plus 2x to the 4, and so on, and so on. So notice how this function has an end behavior that is going from quadrant 3 to quadrant 1, because as x approaches negative infinity, we're going to be going all the way down to quadrant 3, and as x approaches positive infinity, we're going to make all the way up to quadrant 1 over here. Interesting. So now I want to try something here. I want to make it a negative leading coefficient. So right now it's a positive leading coefficient. Let's make it a negative. So if I put a negative here, it just flips the entire thing over. So now we're going from quadrant 1 to quadrant 4. So that's basically how we can use degree and leading coefficients this way. So here is a cool picture I found online, and it's basically kind of a cheat sheet you guys can use whenever you're working through problems. It's really helpful. I found this pretty helpful. Basically, it tells you if a degree is even, basically the end behavior, if you have either a positive or negative leading coefficient, and same thing for odd degrees. If you have an odd degree polynomial, that means your end behavior is going to go from here to here, and if it's a negative leading coefficient, it's going to go here to here. And yeah, I'll see you for the practice video.